Okay, everybody, so in this last part, we will derive this formula for the expected value of a random variable that's defined as a function of x hat, where x hat itself is a continuous random variable with a density of little f. So you'll notice that the formula is very nice because it only involves that density and then the function into which we want to plug x hat. Those are the only things we need to know to calculate this expected value. We don't need to know like the CDF of this new random variable. We don't need to know its density if it has one. It actually will turn out to have one. But we don't need any of those things. Okay? We just need to know those two objects, f and phi. And then with those two objects, we can do two things. We can first of all decide whether phi of x hat is expectable or not. And that's just based on the convergence of the integral. And then the second thing is that the integral, if it does converge, does give the expected value of phi of x hat. So that's very important for things like variance. Because when you calculate the variance, you're supposed to be taking x hat and plugging it into a certain function. And then taking the expected value of that. The function is the function x minus a constant squared, where that constant happens to be the expected value of the original x hat. But that's not so important. The important thing is just that it's some real constant. Okay, so you see that this expression here inside the outermost brackets is phi of x hat. But to calculate this expectation, which is also known as the variance of the original x hat, all you need to know is that function, so that's going to be x minus c squared, and then the density of the original x hat, which, you know, if we know x hat at all, it's going to be through its density. Usually the way we get hold of, the way we represent a random variable is through its density, if it's continuous, if it has a density. So yeah, then all we have to do is calculate this integral, and it turns out that if it converges at all, if this integral converges, then it also represents the expected value. So in other words, it implies two things: the convergence of the integral, the convergence that is of this integral, implies, first of all, that the random variable in question is indeed expectable. It does have an expected value. Okay, and it implies that the expected value of it is the very same integral, that very same integral. Okay, but notice that we don't need to assume the expectability as a hypothesis. The fact that this thing is expectable is a conclusion, not a hypothesis. We don't need to assume it. That would be very bad if we had to assume that as a hypothesis, because in practice, it would be very difficult to verify that hypothesis. You know, if I'm just given some function phi, such as x squared or x cubed or whatever, and I'm given a random variable, how would I verify that this thing was expectable if I didn't already know it? You'd have to calculate the CDF, you know, check that the magic formula it yields convergent integrals, which would mean computing the CDF of that thing. And as you remember from the last video, the CDF of this new thing, phi of x hat, was the function I called g, and it has an extremely complicated formula. It's a formula that we can write down, but it's not a formula that we want to calculate anything with. So it's a very good thing that the expectability of phi of x hat is not actually required as a hypothesis. We don't have to check that in practice. It actually follows as a conclusion. The only thing that has to be checked in practice is just simply the convergence of this integral, or more generally, the convergence of this integral here. Okay, that's all we need. From the convergence of that integral follows the expectability of the random variable here, and then also the fact that this is a true equation, the fact that the expected value is equal to that integral. Both of those follow as conclusions. So the logical structure of this theorem is very favorable to applications. And that is because, once again, both the density f and the function phi will be known in any practical problem. These will both be known, so all you have to do is calculate their product and then integrate that product over the whole real line and just check that it's a convergent integral. And now, you know, checking that a certain integral is convergent is not necessarily the easiest thing in the world, but at least you have a chance because the two functions will be explicitly known to you. And based on that, then you get everything else you want. You know the random variable in question is expectable, and you know exactly what its expected value is. Okay, so we're going to take a look at this theorem. But let me just start by quickly reminding you of what we've done on this topic so far. So first of all, the functions in question are not totally arbitrary, but rather, let me just call them nice. I don't want to use this as like a technical term, but just for the purposes of this video or the sequence of videos, let's allow ourselves to use this term, nice function. So what it means, again, is that you can divide the real line into a finite number of intervals. We can label the division points in increasing order, c1 up to cn, and then we also let c0 represent negative infinity and cn plus 1 represent plus infinity. So we have a number of intervals here which are disjunct in the sense that they are either disjoint or they overlap only at a shared endpoint. And then on these intervals, the function phi is either decreasing or increasing, and it's also continuous everywhere. So no holes or breaks in the graph. And it just alternates. Okay, it can have like a horizontal asymptote, let's say on one end, and it can go to infinity on the other end. Or any combination of those is possible. But yeah, it just alternates between decreasing pieces and then increasing pieces. Like that. Okay, so the whole thing is continuous overall. Oops, partially erased that. Okay, and so yeah, the whole thing is continuous overall, so C0, everywhere on the entire real line. And then also, I'm assuming that the derivatives exist and are continuous, but not on the real line, but just on the interiors. And not only are they continuous, but they're of constant sign. So they're either strictly positive or the derivative is strictly negative also on the interior of each of those intervals. So the derivatives are of constant sign on the interiors. Now notice that at the joining points themselves, like at this point here, it's possible that the derivative could be 0 there. It could have a horizontal tangent. That happens at a joining point. But in the interior of this interval, the derivative is always strictly negative. It's of constant sign. And then in this interval here, in the interior, the derivative is always positive. Strictly. Okay, and they trade off like that. So if there is a 0 derivative, it happens at one of the joining points. So this is basically what I mean by a nice function. Function that looks like this. Now this is very restrictive, obviously. There's a good reason why we're taking such a restrictive class of functions. It's because the more general the class of functions is that you want to allow, the harder it is to prove technical theorems about them. It's already no picnic to prove theorems about this class of functions. But this class of functions certainly covers all the basic cases that we want anyway, such as the squaring function, which is the crucial function for defining variance. And of course, with variance, then you get standard deviation, which is simply the square root of the variance. And that's what's called uncertainty in quantum mechanics. And since that's really the only thing I care about, it's just getting back to quantum mechanics, this is a general enough class of functions for us, for our purposes. Okay, anyway, those are the functions we're working with now. And what we did was we sort of said the following thing. Informally, or initially, we can think of the meaning of this in the following way, that we have an experiment. Remember that in our way of thinking of probability theory, the experiment's always the same. It's what I usually describe as throwing a dart at a one-dimensional dartboard, stretching between 0 and 1, and, in a uniform fashion, so that any subinterval between 0 and 1 of length L has exactly probability L of being hit. Anyway, the outcome is going to be some point omega in that open interval, which we call big omega. And then once we perform the experiment, once we get an outcome, we then take that outcome and plug it into the function x hat. And then we get a real number. And this is what we called the acquisition of a value by the random variable x hat. Right? It acquires a value once we perform the experiment. The mathematical model of that is that we represent the outcome as point in the domain of x hat, omega. And then by plugging that omega into x hat, we get a real value. Because let's remember that a random variable is nothing but a function from the open interval 0 to 1 into the reals. Okay, anyway, so once that acquires a value, you can then take that value and just plug that value into the function phi. And that will give you phi of x hat of omega. In other words, phi composed with x hat, evaluated at omega. And we can say that that's the value acquired by this new random variable on the same experiment, or in the same experiment. Okay, so in that sense, we're defining a new random variable, right? This thing is also a kind of undetermined quantity until we perform the experiment. Once we do perform the experiment and a definite outcome comes out, omega, then the expression acquires a value, which is phi of x hat of omega. And that's some real number, which will be, then the value acquired by that new expression. So does that make it a random variable? Well, no, it doesn't. The problem is that it's not a function of the correct type. If I define it this way as just the composition, so then it will have the correct domain and codomain. Like the composition of these two has the correct domain and the correct codomain to be a random variable. And it also has the left continuity property. It is definitely left continuous. And that's because if I ask what happens at omega minus, sorry, that should be like a little composition sign, circle. Remember that just means we take the limit where we have plugged in omega minus a small positive number. We let epsilon decrease to 0. But because phi is continuous, this outer function here is actually continuous on the entire real line, we can pass the limit sign inside the phi. That limit sign can be passed inside, and you'll get x hat of omega minus epsilon. That is what we just call x hat of omega minus. And then inside here, that's just going to be x hat of omega by the left continuity of x hat as a random variable. Remember that a random variable was defined by us as a function with this domain and this codomain that is both left continuous and non-decreasing. So we know that x hat is left continuous because we know it's a random variable. We're assuming that it is a random variable. So as a random variable, it must be left continuous. Okay, and then you see that the answer inside here is just phi of x hat of omega. In other words, phi composed with x hat at omega. So this quantity we started out with turns out to equal the same function, but with omega itself plugged in. And that gives the left continuity. That gives the left continuity. So it has the correct domain and the correct codomain. And it has left continuity. But what it doesn't necessarily have is it's not necessarily non-decreasing. Okay, this function here is not necessarily a non-decreasing function, which it needs to be to count technically as a random variable. Okay, so therefore it's not necessarily actually a random variable in the technical sense. It is some kind of random quantity that acquires a value when you perform the experiment, right? That value being, again, phi of x hat of omega. But it doesn't count as a random variable because it just doesn't have the technical properties that a random variable is supposed to have in our approach. Now notice that I said not necessarily, right? It's not necessarily non-decreasing, but it could be non-decreasing. Namely, I'll tell you the case where it is. If our nice function has only one piece, one interval, from minus infinity all the way to plus infinity in one jump, and if it's just an increasing piece, let's say just a green piece, oops, the whole function's graph is just like a green piece. So the function, therefore, is increasing, and then since x hat is also non-decreasing, when you have a composition of two non-decreasing functions, that result will also be non-decreasing. So yeah, we could actually get a random variable, but it just doesn't always happen. It happens in this picture here, which is a very simple case, where you have no division points on the x-axis. Okay, so question is, what if we do have division points? What if the picture looks a little more complicated and looks like this? Now, then the argument doesn't work. We don't get something that's like technically a random variable. Okay, so the approach we took was like this. We first said, well, we can look at that composition, and we can ask, when does it take a value, or when does it acquire a value less than or equal to a? If we take all outcomes, omega, between 0 and 1, for which that happens, we can hope to calculate the probability of that. Okay, this is some event. It's going to depend on a, so let me call it e sub a. And again, I'm not going to assume it's an event. We would have to show that it's an event, because not everything is an event. Not every set of outcomes counts as an event. To count as an event, it has to have a probability. So I'll just put it with a question mark. Okay, but it's some event that depends on the value of a. And by computing the probability of it, we can define a function, g of a, where a is just an arbitrary real number. So that will define some function, right? And that would be the CDF of this thing if it was a random variable. See, this thing is not technically a random variable because it's not necessarily non-decreasing. But if it was technically a random variable, then this g would be exactly the CDF of it, because the event in question is just the event that random variable acquires a value less than or equal to a, and the probability of that is the CDF. Okay, so even though it's not necessarily a random variable, there's nothing preventing us from calculating this probability and using it to define a function g. Okay, now what can we say about that function g? Well, it turns out that function g turns out to be a valid CDF in the sense that it maps the reals into the closed interval 0 to 1. It's non-decreasing. It's right continuous. And it's exhaustive. So it has all the correct behaviors to be a CDF. The question is just, what is it the CDF of? Okay? And what it's the CDF of is a very simple thing for us to answer now. All you do is you take g itself and take its pseudo-inverse and restrict it to the open interval 0 to 1. That gives a random variable, which we can call temporarily y hat. This is the associated random variable to g. Because remember that every single valid CDF that exists has a unique associated random variable. Okay? And the CDF of y hat is g, in the sense that if we calculate the probability that y hat acquires a value less than or equal to a, we'll just get g of a again for all values of a in the reals. Okay, so that random variable y hat is a genuine random variable. It's like, from a technical standpoint, it meets all the requirements of a random variable. Whereas this thing here did not, simply because it failed to be non-decreasing. But y hat will be non-decreasing. And it will still have that same CDF. So it makes sense then to declare y hat to be the new meaning. We're going to take y hat, in other words, to be the new and improved meaning of phi of x hat. Okay, so in other words, the idea is that then we replace the original notion. We had this informal or naive definition. We sort of had this initial definition that phi of x hat, maybe I should state the definition this way. Phi of x hat is a function whose value at omega is, by definition, this. Right, so that was our naive definition. And that definition didn't turn out to work, at least not in all cases. Like, it works fine in this case here. But it doesn't work very well in more general cases. Okay, so, but now we have a new definition, or new meaning that we can give to phi of x hat. Namely, it's just this y hat, which is the associated random variable of this g, under this one-to-one correspondence between CDFs and random variables, which is, the pseudo-inversion process we talked about at length in prior videos. So yeah, the new definition, which is the ultimate one, is that phi of x hat is going to be defined as the pseudo-inverse of g, restricted to the open interval 0 to 1, where g is that function, g of x, or g of y, I think I called it in the last video, by definition is some function which we worked out. Like, we worked out by computing this probability. Okay. Now, the calculation isn't fully worked out in a prior video. I'll just tell you the final formula for it. The final formula was something like this. You sum over all n for which y belongs to the range of phi n. And you're going to be summing big F of phi n inverse of y minus big F of c n minus 1 in the increasing case. Let me just symbolize it this way for brevity. That's the case of like a green piece where the function phi sub n is increasing strictly. And in the other case, the decreasing case, it's going to be f of cn minus f upper minus of phi n inverse of y. Okay, so there are two cases, depending on whether the interval in question, like the subscript n, designates an interval where the function is increasing strictly, or whether that n designates an interval where the function is decreasing, one of the red pieces. Okay, and then there's other terms I call type 2 terms, all n for which y is strictly above the range of phi n, and then we had just had f of cn minus f of cn minus 1. So that was the formula. It's a very complicated formula, but we did check that this g is a valid CDF. We checked in the last video that this g is a valid CDF. Okay, we found that it does indeed map the reals into the interval 0 to 1 closed. It is non-decreasing. Right continuous. Okay, now my proof of right continuity was a bit flawed. I should really just put a little asterisk on this, because I can go back now and just correct it a bit. And then exhaustive. Okay, so the proof of exhaustiveness was perfectly good in the last video. The proof that it has this domain and codomain was perfectly good, and the proof of non-decreasing was, again, perfectly good. Proof of right continuity has a slight flaw, which I'll fix now. But it does ultimately work out. So yes, it is a valid CDF, and then we know that its pseudo-inverse, restricted to the interval 0 to 1, is therefore a legitimate random variable. Okay, and notice that it has the same CDF. It's a random variable with its CDF being g. And that's the CDF we wanted it to have, because that's the same CDF that this thing here would have had if it was a random variable. See, that thing there is not necessarily a random variable in the technical sense, but it does have a CDF in the sense of the function that measures this probability, the function that measures the probability of this event. Kind of would be the CDF if it was a random variable. Now, it's not a random variable, but nevertheless, we've now constructed a new random variable that does have that same CDF. Okay, so we've managed to construct something that is genuinely a random variable in the technical sense, and it has this correct CDF. It gives the correct probability. In other words, it gives this theorem that the probability that this newly constructed random variable is less than or equal to a is indeed g of a for all real a. Okay, and that's what we want. We want this probabilistic relationship to hold true, because that's the same probabilistic relationship that would have held true if phi of x hat meant this composition, which would be like the naive initial way of thinking about it. Okay, good. So that's roughly what we did, but I should just remind you what was involved in this calculation. Okay, because it was a pretty laborious calculation, and I want you to see that it really is technically correct. So what was involved in that calculation? We had to calculate the probability of this event. All right, the first thing we did was we basically wrote that event as a union. something like that, it's going to be a finite union. And these are like pairwise disjoint events. So what were these events? So like E sub A is the event that phi composed with x hat takes a value less than or equal to A. And then E sub A, let's say 1, is going to be the event that same thing happens, but at the same time, x hat acquires a value between C0 and C1. And then E sub A2 would be, again, probability that the same thing happens. And at the same time, x hat acquires a value greater than C1, but less than or equal to C2. So on and so on. The last one would have the same circumstance, and the fact that x hat is between Cn and Cn plus 1. Okay. Now actually, this greater than or equal to here doesn't really have to be written that way. It could just be written as less than, because this is actually plus infinity, and x hat is real, always acquires a real value. So certainly it will be strictly less than, plus infinity, but it does no harm to say less than or equal. And since it's written as less than or equal to in all the other cases, we may as well write it as less than or equal to in that case as well, just for uniformity of notation. Okay, anyway, so yeah, notice that these are pairwise disjoint. These events here are pairwise disjoint. Okay, and then also notice that, well, their union is just E sub A again, because those ranges from like Cn minus 1 open to Cn closed, the union of all of them over all n is just all reals. That's just a subdivision of the entire real line. And since x hat must be on the real line, it must be in at least one of those intervals. So it's so far a correct calculation that we've done here. Okay. Now, by the Kolmogorov axiom of countable additivity, and this actually is even simpler than that, it's just finite additivity, because we only have a finite collection of sets here. And they're pairwise disjoint. We could, in fact, have a countable union of pairwise disjoint sets, as long as they're all events. Now, I haven't really checked yet that they're all actually events. So we should ask ourselves, do we know that these are events? Do we know that these actually have probabilities? Okay, well, we do, because, you see, now it's acceptable to put a subscript of 1 here, and a subscript of 2 here, and a subscript of n plus 1 here. Because if we know that x hat has acquired a value in this interval, now on that interval, remember that phi coincides with phi 1. Remember that phi 1 is just a notation for this first piece of the function, with its own domain, which goes from C0 to C1. Phi 2 is a notation for the second piece of the function, whose domain is this. Okay, so on that interval, the function phi just coincides with phi sub n, where n is the subscript in question. Okay, and now notice that all of these compositions are monotone functions. Every single one of these compositions that appear here are monotone. That is, they are either non-decreasing or non-increasing. All right, why is that? Well, x hat is monotone. X hat is non-decreasing as a random variable. And then phi 1 is either increasing or decreasing. Phi 2 is either increasing or decreasing, right? So we have the composition of two monotone functions, which is always a monotone function. And then we have like the sub-level set. This thing here is like denoting a sub-level set. So it's like all points, or all input points where the function's value is less than or equal to A. Now, if you think about like a non-decreasing function, the sub-level set at height level A is just going to be everything to the left of a certain point, possibly including that point, possibly excluding that point, depending on the continuity. But and then also, if you have a decrease or like a non-increasing function, let's say I have some non-increasing function, a sub-level set less than or equal to level A is going to be everything to the right of some point, possibly including or possibly excluding that point. But see, both of those are just intervals, and intervals have probabilities. Under our model, you'll recall that we never fully specified the probability model. We only partially specified it. We partially specified it by saying that all sub-intervals of the open interval 0 to 1 have probabilities, which are their lengths. And then, of course, a union of intervals, a countable union, will have to also have a length, but we didn't say how to construct that. Because, if you have countably infinite number of intervals, it's not so easy to say what the length is. For a finite union of intervals, which are disjoint, then the length is easy to define. It's just like the sum of the lengths of all the pieces. But if you have an infinite number of pieces, and if the pieces overlap, it's not so easy to define what the length of that type of set is. That's what measure theory is all about. Lebesgue measure is a kind of generalization of length to more complicated sets on the real line. But we didn't work with any of that. We didn't deal with any of that. We just partially specified the probability model by saying that an interval has a length, which is its probability, by definition. Well, see, all these sub-level sets now are intervals. Every single one of these sub-level sets is just either an open interval or a closed interval. So those all have probabilities. Okay, and we also know that these things are events. These, let me do that in some other color, gray. Right? This type of thing is an event because basically it's a sub-level set of a random variable, and then you get rid of another sublevel set of the same random variable, something like that. And since the family of events is closed under subtraction, that is also going to be an event. Okay, in fact, it's even better than that. It's an interval, because you're basically taking, like x hat is some non-decreasing function, and you're taking a sublevel set, like less than or equal to C1, and then getting rid of another sublevel set down here, less than or equal to C0. Now what's left is just going to be like this interval here. And we don't know if it's open or closed at the ends, but it doesn't matter, it's still an interval. And then of course we're intersecting. We have like something that is an event here. It's the sublevel set of a monotone function, so it's certainly an event. And then we have something here, which is another event. And then the conjunction, is just intersecting the two. Okay, and in fact, it's even better than that, because it's the intersection of two intervals. Both of these events are actually just intervals. They're very, very simple kinds of events. So I probably should indicate that. This is actually some interval. We don't know if it's open or closed. This also is an interval. Again, we don't know if it's open or closed at its two ends. And then we're just intersecting those two intervals. Now, what can we say about the intersection of two intervals? Intervals don't behave very nicely under unions, because if you take two disjoint intervals and take their union, it's no longer an interval. But intervals do behave beautifully under intersections, because the intersection of two intervals is either the empty set, which is also an interval. You can think of the empty set as the interval, let's say, open interval from 0 to 0. Right? Or, if the two intervals overlap, then their intersection is another interval. So you see that this whole event here is actually an interval, or the empty set, which also counts as an interval in a kind of degenerate way. And the same will be true of this. It's an interval, possibly degenerate in the sense of being empty. And then all of them are like that. They're all essentially just intervals. So they really are events. Okay, and then by countable additivity, which we know is going to have to be true in any probability theory. Now, again, remember, we don't actually know that our probability model has that property. That's part of Lebesgue theory, is verifying that once you define generalized length, like once you define the length of any set on the real line, you then have to check that that notion of length has the countable additivity property, and therefore can be used as a Kolmogorov probability model. We don't know that. But nevertheless, we know that ultimately, if this model is going to work at all, it's going to have to eventually satisfy the Kolmogorov axioms. So since this whole calculation is just aspirational anyway, remember what I mean by that, is that this whole calculation is serving only to help us understand or check that this is the correct function that we want to use as our CDF. And then all we do is pseudo-invert that to get our random variable. But where that function comes from, why that's the formula that we want, that's what this calculation is meant to reveal to us. So the calculation is not meant to prove anything, really. It's really just meant to help us discover the correct formula for G. So it's okay to use something that we haven't proven, simply because this is like an aside. We're doing this as a little aside. All right, but anyway, by countable additivity, we then get the sum. The probability of the union is going to be the sum of these probabilities. Okay, and then from there, you remember the argument, roughly. We had to divide the terms into, I guess I should use little n. We had to divide the terms into those where y was in the range, those terms in which y was greater than, or fully above the range of that piece, and then those terms where y was fully below the range of that piece. Okay, so these probabilities all turned out to be 0 because these sets are actually just empty. So those were like what I call the type 3 terms. They all just zero out. Right, these were the type 2 terms. And in those, what ends up happening is that like this condition here turns out to be irrelevant because it's just implied by this condition. So in other words, these inequalities on x hat already imply this inequality. And therefore you don't have to list both of them in the conjunction. The conjunct that's implied by the other conjunct is redundant. You can delete it. And so those events really just turn out to be this event here. We know how to compute the probability of that. It's f of cn plus 1 minus f of cn, something like that. So we got these type 2 probabilities, and they just turn out to look like this. All right, and then with the type 1, there were like two cases we had to investigate. There's the case where the phi n piece is strictly increasing, and then the other case where it's strictly decreasing. And there were slightly different answers in the two cases. So anyway, that was the calculation, in a nutshell, that gave rise to this very complicated looking formula. Here you see the type 2 pieces. The type 3 pieces are absent because they're all 0. And the type 1 pieces they have two cases, right? Depending on whether that piece of the curve is increasing or decreasing. Okay. So anyway, that's where we got that formula from. Now, I also mentioned that there was a slight flaw in my verification in the last video of the right continuity of G. Now, the reason I want to talk about this is both to correct the record on that, okay, but also to develop a good tool for discussing the continuity of G. in the case when f is continuous. So it's going to turn out that if big F is continuous everywhere, that's going to turn out to imply that big G is also continuous everywhere. And I actually mentioned that in the last video, but I didn't really prove it. I just kind of gave you a hand-wavy argument about, losing a type 2 term and picking up a type 1 term that's very close to it. But yeah, we can be more precise, and we should try to be more precise about things like that. So I'm going to just talk about this for a second. Okay, it's a pretty simple idea. We can calculate g of y plus epsilon minus g of y, where epsilon is some positive number that's going to be very small. And I can sort of make it small enough for something nice to happen. But I want to develop a formula for this difference. And this is going to help me study the right continuity of G in general, like under all circumstances, and then the continuity of G in the case when big F is continuous. Okay, well, I'll show you the idea. The idea is, graphically, it's very simple. Remember that we've got these pieces that are trading off between increasing and decreasing. And then we have a height level y. Actually, let me draw the height level y plus epsilon first. I'm going to leave myself a bit of room to play with this picture. Okay, and then there's this other height level, which I'll draw dotted, which is going to be y. Okay, see, various things can happen. Like you can have a piece that kind of looks like this. Maybe have something like this. Okay, and in particular, I want to focus on this little bump that's sort of between those two lines. I claim that we can just eliminate that by taking epsilon small. You see, there's only a finite number of those bumps, because there's only a finite number of intervals in the first place. The red and green, like pieces of the function, there's only a finite number of those pieces. And each piece is very simple. Each piece is either strictly increasing or strictly decreasing. So there can only be a finite number of those bumps that are sort of between my two blue lines. Can have several of them, but there's only a finite number of them. And why that's good is because by taking epsilon small enough, you make those two parallel blue lines so close together that you can just eliminate the bumps, you see? But I'm going to make this y plus epsilon so close to y that now I don't have any bumps between the two lines anymore. So by making epsilon smaller, in other words. So this would be a problem if you had an infinite number of bumps to account for, because then you wouldn't know, like maybe you have to make it within like epsilon 1 of y to eliminate bump number 1, and then you have to make it within epsilon 2 of y to eliminate bump number 2, and so on. But if you had an infinite number of bumps, then you might have like an infinite sequence of epsilons that approach 0. And so then you couldn't stop at any finite point. Like the top line would have to be pushed all the way down to the level y. But that doesn't happen here because we only have a finite number of these bumps to worry about. So you just take the one of like smallest height. And, So anyway, the point is that by making epsilon sufficiently small and positive, we can eliminate that picture where there's a kind of bump. What I mean by a bump is one of these joining points that lies between, somewhere below this top line and above this bottom line. Okay. So now, this difference here is just going to represent following thing. Okay, let me draw the x-axis down here somewhere. If I take these 2 points, I'm going to look at the change in f on that little interval. Okay, then I take these next 2 points and look at the change in f on that little interval. Then I have these next 2 points. And then big F has a change on that interval. Okay, now, so what's happening here? Okay, actually, before I go any further with that, it's probably helpful just to remember how G is defined, not in terms of its formula, which we know, right? We have the formula written out here. Let's see, right here. And this formula is precise, but it's not that illuminating in terms of revealing the actual meaning of G. But we did discuss the actual meaning of G in a prior video, and I'll just remind you about it. It goes something like this. So suppose I have my nice function. Let's just say it looks something like that. Well, let me just draw a few more pieces. Okay, and then I've got my height level y, like that. So the basic idea about the quantity g of y is that it represents the total change in f over intervals in the sub-level set at level y. That's roughly what the function g of y measures in words. Okay, so let me just draw you a picture of this. So we look at the sub-level set. That means that we're looking at places where the graph intersects the height level y, and we look at the corresponding x value. And let me just label those in increasing order. So you see this one is an interesting case because it represents a point of tangency between the graph of the function phi and the horizontal line at height level y. And that can happen. And then here we have last one. So there's only a finite number of these points, simply because there's only finitely many pieces, and each piece is a one-to-one function. Each green or red piece is strictly increasing or strictly decreasing, and so therefore can only cut a horizontal line at most once. So we have this finite collection of x values, and what we're doing is we're essentially taking all the parts of the real line that are where the graph is less than or equal to y in height. So let me mark those in yellow. Here's one such interval. Here's another one. Here's another one, and that's it. You see, these intervals here, like this gray one, the function's height is above y. And then also in this gray interval here, right, you can see that the function's height, whether it be this green piece or this red piece, would be above the height level y. And then similarly for this interval here, the function's height is above the height level y. So we're just looking at all the pieces of the real line between those x values that are less than, where the function's height, phi, is less than or equal to y. That's called a sublevel set. It's like the set of x's where phi of x is less than or equal to y. And that's basically just the union of a finite number of intervals. Okay, now you should bear in mind that some of these intervals could be, well, two of these intervals could potentially be unbounded intervals. For example, if the last piece, let me just extend this picture a little bit. Let's say the last piece of the function phi is actually decreasing, and like it decreases unboundedly all the way to minus infinity as you keep moving right. So like this part wouldn't be, oops, not that, sorry, I want to do that in red. This part up here wouldn't be counted, but then we would have this x6, and notice that then this whole interval from x6 all the way to plus infinity would be counted, because the function's graph is below, or less than or equal to, the height level y. So yeah, you have basically a union of these intervals, and at most two of these intervals are unbounded. Those are the two on the ends. I can label x0 as minus infinity, and let's say x7 as plus infinity, just to be able to denote these intervals. So this is going to be like the union of a certain collection of closed intervals. And they're closed intervals because of the continuity. Notice that the actual value y is being included, the actual height y, because it's a less than or equal to. So by continuity, we can go all the way up to either of the endpoints, including the endpoint itself. And the height level will be less than or equal to y. But basically it's like xk minus 1 to xk, closed interval, over a certain finite collection of k values. But it's not all of them. Okay, so yeah, it's not all the k values we're taking. It's all the k values in some set, which depends on y. So let me call it like s sub y. So, like, for example, in the picture that is drawn here, what's the s sub y? Well, it would be like 2, because the interval from x1 to x2 is included. It would also have 4, because the interval from x3 to x4 is included. It would have 5 in it, because the interval from x4 to x5 is in there. And then it would also have 7 in it, because the interval from x6 to x7, which happens to be plus infinity. But anyway, for k values in that set, you take the union of those intervals. And then we're just looking at the total change in f. So what that means is like f at the right endpoint, so okay, it's the sum. And you'll take f at the right endpoint, which is, let's say, xk, and subtract away f at the left endpoint. And we need an upper minus here on this one. Right, and k is going to run through that set, s sub y. So that's what I mean. That's what I mean by the total change. Okay, let me take a moment to just comment about this upper minus here. So we need that because that's there in the formula, if you look back. And there was good reason for that, as we showed when we derived this expression for g using the rules of probability. Like this upper minus has to be there. And you see that upper minus is only associated with terms that are being subtracted, only when f is being subtracted. So anytime you have an upper minus, it has to have a minus in front of it. That's the only time that actually occurs. So when you come to this expression, you can see why it's only when you have this minus here that you have this upper minus. But you see that upper minus is going to disappear if this happens to be a continuity point of big F. Because at a continuity point, right, so if big F is continuous, C0 here, at xk minus 1, then f upper minus is just the same as f at that point. So then you'll just get the traditional delta f, which is f at the right endpoint minus f at the left endpoint. Okay, but if the function capital F happens to be discontinuous at this point, if that's like a jump discontinuity, a jump point of big F, then you have to put the upper minus. So you have to reinterpret this change in f to mean that with the upper minus there. But the upper minus is always correct, because the upper minus just disappears when that point is a continuity point for big F. Okay, now you might be thinking, well, what happened to all those other terms, like the type 1 terms and the type 2 terms? How is this a correct formula? Let me just fix the formula here. Okay, so those terms are there. They just telescope away. Now, let me show you an illustration of that. For example, Before I say that, I should also mention that if you look at those k's that are included in the set S sub y, you'll notice something. You'll notice that the interval. So, for example, let's look at this interval here, just as an illustration of this general comment. Okay, the k in that case is 4, because I'm labeling it after the right-hand endpoint. So this subscript here would be k minus 1. Now notice that k minus 1 is always going to be on a red piece, which means that before that, x3, the function's height is above, because that's a decreasing piece. Right, the red pieces are decreasing, so if you look just to the left of x3, the function's height is above that horizontal line. So that's not included. Okay, if we look at another value in that set, it will be similar. For example, if you look at 7, right? Look at k equals 7. You take k minus 1, which is 6, and you'll see that that point is on a red piece. So if you go just to the left of that point, the function is above. So it's not in that sublevel set. Okay, so yeah, even in the case k equals 5, for instance, right? Over here in this interval, k minus 1 would be 4, and that point is also on a red piece. Now, of course, that point is also on a green piece, but that doesn't mean it isn't also on that red piece. Actually, that term just telescopes away. No, I'm wrong about that. I'm sorry, it doesn't telescope away. What happens is, that's actually a very good thing to look at right now. So what's going to happen is, there's going to be a term corresponding to k equals 5, which is going to be f of x5 minus f minus of x4. And there's going to be also a term corresponding to k equals 4. So I'm talking about a case where the two k values are consecutive, as they are here, 4 and 5. So there's going to be a term also corresponding to k equals 4, which is going to look like this, f of x4 minus f minus of x3. Now you'll notice that these two don't exactly telescope away. Rather, what you get is the jump in the function f. Let me write it this way. At that point, x4. It's the function's value at that point minus like the left-hand limit. So that's exactly the jump value. Now that could be 0 if x4 happens to be a continuity point of big F. But if x4 is one of those jump discontinuity points, then the jump value could be positive there. And that's okay, we want that. We want that because that point is going to be a point of positive mass. And we want the mass of that to be included. Because notice that that point is actually in the sublevel set. That point there is actually in this sublevel set, because the height is less than or equal to y. So that point is okay, and we want if that's a point of positive mass, we want to include that positive mass, like in the calculation of g of y. So it doesn't exactly telescope away unless x4 is a continuity point. But if it's a jump discontinuity point, a jump point of big F, then it just contributes its positive mass automatically to this sum. Okay, so anyway, that's a good way of understanding. Now, what happened to all of these terms? Like, what happened to here, like this f of cn or this f of cn minus 1? The answer is those just telescope away from one term to the next. They cancel each other out. You can look at it in this picture and you'll see it right away. Okay, for example, one of the type 1 terms is going to be, let's see if I can find a color I haven't really used too much here. Maybe I'll do it in blue. Okay, so one of the terms is going to come from this increasing piece right here, and it's going to be this value, which happens to be x2, minus this, which is a joining point. That's like the point c1. Remember, c naught is minus infinity. And the first point where a red piece joins to a green piece is going to be c1. So we're going to look at the change in f from x2 to c1. That's going to be a type 1 term corresponding to that green piece. But there's no c1 in this expression. There's no f of c1 in there. So where did that go? Okay, well, there's also this red piece, right? This red piece here. And coming from that red piece, there's also a type 1 term, which is f of c1 minus f of this point here, which is x1, well, upper minus. So you see, when you add those two terms together, because they both appear as type 1 terms, the f of c1 will just cancel additively. And all you'll be left with is f of x2 minus f upper minus of x1, which exactly appears here. So you see that the c1 just basically cancels out. It sort of telescopes away. And the same is going to be true of all those joining points. Like this one here is going to be c2. The only time a joining point doesn't telescope away like that is when one of the c's coincides with one of the x's, as happens here with x4. See, let's label everything. So that's the point c2. The next joining point happens to be right here at 0. That would be c3. And then x4 is also c4. That's a joining point between a green piece and a red piece. And we already talked about what happens there. It doesn't quite telescope away, but rather the jump in f at that point gets contributed, which is non-negative. It could be 0, but it could be positive, depending on whether big F is continuous at that point or not. Okay. But anyway, this is a correct formula for g of y, and this is a much easier formula to work with. Okay, so coming back to this question of g of y plus epsilon minus g of y, the thing to notice is that sublevel sets of phi, if I look at all x's where phi is less than or equal to y, right, that's going to be inside all x's where phi is less than or equal to y plus epsilon. Because if phi of x has a value that's already less than or equal to y, then certainly it's less than y plus epsilon as well. And so the change in f on this set, if I look at, let me write it this way, like the change in f on this set, because f is a non-decreasing function, it follows that the change in f on that set is less than or equal to the change in f on this set, this larger set, because this larger set includes the smaller set. So however much f changes positively on that smaller set, it changes by at least that much on that larger set. Okay, and then you can see also that the difference between the two is just going to be something like it's bounded by, we can only bound its absolute value by a sum of terms, where those terms are just the absolute changes on these little difference intervals. See, the two level sets differ by a bunch of intervals. Let me see if I can draw this in some colors here. If I look at the upper line, the line with height y plus epsilon, so the sub-level set for that, let me do in yellow. So that's like, it's going to include this interval here, and then all the rest of it. So that's the sub-level set for the height y plus epsilon. Okay, and then let me do in some other color, like gray, the sub-level set for the height y. That's going to include like this piece here, and then this piece here. So the gray one is the sub-level set for the height level y. And you can see that the gray one is inside the yellow one. That's the thing I was saying here. The gray one is a subset of the yellow one. But you see that the change in f on the yellow set minus the change in f on the gray set is bounded in absolute value by the absolute changes in f on all these little differences, all these little pieces, these intervals, which represent the set difference. So you see, if I take one level set, the yellow one, and subtract away, delete the gray level set, I'm just left with a union of a bunch of little intervals. And if I look at the changes in f, absolute values of them, the sum of those gives like an upper bound. So take the absolute changes. Okay, it's a little hard to label this because I'd have to like label all these points to get precise notation for this. But maybe I'll just say, kind of loosely speaking, I'll take the change in f on each little interval, and I'll just sum over all those little intervals. And by those intervals, what I mean is that if I take the level set where phi is less than or equal to y plus epsilon, that sub-level set, I mean, and subtract away the sub-level set where phi is less than or equal to y, the resulting set is a union of intervals. Let's say I sub j. Finite union of intervals. We just look at the changes in f. And again, by the change in f, I really mean f at the right endpoint minus f upper minus at the left endpoint. I'm always using that notion of change in f. Okay, well, what can we say about that upper bound? I mean, certainly we have 0 as a lower bound, because it's an absolute value. Now, what can we say about that upper bound? Okay, so just to clarify, right, I can sum over j. And the I sub j's I'm talking about are things like this, and then this, all these little intervals here. Okay, and there's only going to be a finite number of those, because there's only a finite number of the red and green pieces of the function phi.